Again, weren't those student presentations amazing? It's great to see all the breadth of things going on. So our propagation radiation group is very diverse. We have a couple different things we're talking about today. So I'm fortunate to be the group leader. My name is Vic Sparrow, and these are some of the faculty members involved. And can I advance the slides? I can. Okay, so it's the big arrow. Again, we have a number of students who are currently working on projects and with a lot of different faculty members. And again, we're so pleased. Today, we're just going to give you a couple quick highlights of some of the different things going on in the group. We're going to start off with Dr. Steve Thompson talking a little bit about the program Senscape and what you can do with it. It'll be followed by Dr. Michelle Vijan to give you an update on sprawl. And then I'll talk about ATV predictions in one of the state parks here in Pennsylvania. So let's get rid of this PowerPoint, and we'll go on to number 2 for Dr. Thompson. Dr. Thompson, come on up. Yep, we're done with these slides. Number 2, please.
Well, that's coming up. If one of the students could please send an email to Max Pagnucco, tell him I'll be about a half hour late for my class, but I will be there. Okay, so I'm going to talk about a way to model acoustic systems that I use for a lot of things having to do with transducers, but systems that are bigger than just transducers. The last one will be the clarinet. This, for example, is a system, is a model for a basic moving coil loudspeaker. It follows the model which is often used in analog circuit modeling, where you have an inductor and a resistor at the beginning, you have a mass spring system in the middle, and it couples to the acoustics at the end. The thing that Senscape makes easy is adding extra code to analog circuit models, things that can be done in ordinary differential equations, so that you can add in, for example, nonlinearities in the different parts of the system. You can have a nonlinear spring, a nonlinear K of X, and different things can be made nonlinear. Another system that is fairly straightforward is flexural beams. It's long been known that you can do a transmission line model for a simple linear transmission line, but making that into something that deals with the rigidity of thin beams simply means changing the way the stiffness of the spring is calculated to include the rotational bending and the flexural stiffness. That's part of the PhD work of Carter Childs, but he's been doing that. At the bottom is a cantilever beam using that kind of a model. This is a model of a balanced armature loudspeaker that is the kind of thing that traditionally was used only in hearing aids, but in the last couple of decades has been used more and more in the high-end in-ear monitors that are used for like stage monitors and things like that. This includes an electrical drive. The pink part is a magnetic circuit. The magnetic circuit is a very important part of the design of this thing. The green is the mechanical system, and it would then go on to an acoustical system. Things like this are fairly straightforward. Now, this is the one that I wanted to spend a little bit of time on. And for the people back there, I hope that this is set up. I do have this set so that it's going to play a sound file at the end. But the clarinet model is the most of the parts on the right are tube models for the closed part of the tube, and then open tone holes that radiate out into the air. That's all linear acoustics, but it includes thermoviscous, an accurate model of thermoviscous modeling in the tubes. The reed is modeled simply as a simple linear harmonic oscillator. a cantilever beam that opens and closes and allows air to flow through. The airflow through the reed follows the nonlinear function, the highly nonlinear function, because as you increase the blowing pressure, not only do you increase the flow through the reed, but you also tend to close the reed. And that creates a very significant nonlinear function that actually allows the system to begin to oscillate on its own. This model is also set up so that the tone holes can be individually opened and closed, so that we actually can play something. Figuring out how to continuously vary the impedance as you open and close the holes was a little bit of a challenge, but that is purely done with the computational things, with only at the input end, the energy is supplied by a constant blowing pressure, and you change the open and closed tone holes. So this is the kind of thing that can be done, and I will now pass it on to the next person, Dr. Vigeant.
Thank you.
The arrow advances.
All right, thank you. Hello, my name is Michelle Vigeant. The name of my research group is the Sound Perception and Room Acoustics Laboratory. Lab refers to the people. My actual physical lab has a different name. So my general overall theme is how do we relate good acoustics, something that is good perceptually or works well cognitively, doesn't distract you when you're trying to work, for example, and also physiologically, does it cause increased stress levels in manufacturing facilities, that it could cause hearing damage, that type of thing. And the overall goal is how do we link the two? And so my research centers around trying to come up with numerical values that we can quantify the sound field to try to have a way of predicting for designing and assessing spaces to know the, is there a laser pointer? The human response. So in general, for the research that we do, we use this physical space, the oralization and reproduction of acoustic sound fields, or the ORIS facility. If you participated in last year's workshop, there was a video that talked about this facility, and it's linked on my website. And so this facility consists of 30 2-way loudspeakers and 2 subwoofers. And these 30 speakers are arranged as shown, with 12 in the dimension around the ears where a person is sitting, with 8 at 30 degrees below, 8 30 degrees above, and then 2 nearly overhead at 60 degrees. And we would have them a bit higher if the facility was a larger space, but it isn't. However, I'm not sure if the new buildings have been discussed, but we're getting new engineering buildings and a new, bigger anechoic chamber, and it's going to be coupled with the reverberation chamber as we currently have. So that we use this space using a method called ambisonics to reproduce sound fields three-dimensionally, and we can do this for various various types of spaces. So we currently have concert hall research where we are reproducing measured concert halls, and then we've made changes to those signals so that we can find out the smallest difference people can hear, the just noticeable difference of reverberance. And so we took measured signals and changed them and had people evaluate them. We're currently doing some work with binaural sound reproduction, so different methods that can be used to process sounds to then have a best 2D or 2-ear reproduction that still tries to maintain spatial perception. And then the third area of research that we're currently working on is looking at how acoustics of office spaces, the type of noise that we might have in those spaces, affects our abilities to work, also our subjective response and physiological response. So this project currently has 2 students working on it. Zhou Zhao, who's an MS student and will be graduating soon, and Olivia Hui Young Park, who has just started on the project. And I'll just talk briefly about this project. So in this, for Zhou's project, we have a simulated office environment that has various types of noise. We have intermittent noises, which include phone ringing, conversations, which are particularly distracting, and and office equipment noise. And that is our one scenario where we have lots of these intermittent noises to simulate a person sitting in an open office with various other people around them making noise. And then our other situation is where we have relatively high, about not too awful, but certainly noticeable HVAC noise at about 45 dBA. And what we do is we have people come in and have these various acoustic conditions. They need to do a series of cognitive tasks so we can see the effect on their memory, attention, and other aspects under the different environments. They also give us ratings, how distracting, how annoying, how much they think this might affect their productivity if they had to work in this environment daily. And lastly, we also are getting some physiological data where we're measuring heart rate and how that changes with time and how we might see differences in stress levels depending on the environment. So this project is underway with data collection now just beginning. This is a continuation of a previous project where we, in addition, we did measure heart rate. We also measured skin conductance, or known as electrodermal activity. So the salinity on our fingertips changes as our stress or arousal level changes. And in this case, we had both the HVAC noise and the intermittent noises with different balances. So we had one extreme where it was very high levels of intermittent and less levels of HVAC, and then vice versa. And what we found was that the order 2 people, so in red, they were the ones that began with that balance shown there, with the intermittent levels quite high and the HVAC levels lower. And as they moved to higher masking levels or higher HVAC levels, and this is showing the acoustic environment, which is also showing time, that their stress levels actually decreased, and the other people, their levels increased. So we saw in the sense that the case with higher intermittent noise seemed to be more problematic than the other way around. So our next step here is to add in measuring brain activity using a 14-channel EEG system. And so it's this brand is Emotive, and it's a headset that looks like that. Each pad, there's felt pads for each electrode that get soaked in a saline solution, and then that allows for conductivity. The software that it comes with us gives us a good way of checking how well it's connected and the data quality, and then we can get this series of output then can be analyzed by using different wavelengths to measure for things such as attention or distraction, and that type. Attentiveness is one of them. So that is everything. So thank you, and Dr. Sparrow can wrap up for the group.
So now on to 4. Okay, so I would like to thank Dr. Thompson and Dr. Vijan. One of the things about us being in the pandemic is there are some students who not only did their work and completed it before we had this next workshop. It's just how it worked out. One of those I wanted to highlight a little bit is a former student of mine, Edwait Ambeskar. He graduated very recently in the summer, and he also completed gave a nice presentation at the Internoise meeting. So I wanted to just give you some highlights of a little bit about what he worked on. And at Wait, also we have collaborated with people in the Department of Recreation, Parks, and Tourism Management. And there's a postdoc over there, Nathan Rigner, who was also involved with this work. So we'd like to thank him as well. So again, this is an issue which is directly related to acoustic propagation. And the idea is that we've developed a set of software which is open source, excuse me, in Python, so that anyone can have this software, and wanted to show you a little bit about what it can do. So again, the issues are related to natural quiet. When people go to a park, they very often expect that the noise that they hear is either going to enhance or be a problem for their pleasure. And the idea is that some people like to go into natural parks and bring things with them, like all-terrain vehicles or things like that. So some people love the ATVs. Other people don't love the ATVs, depending on what they're looking forward to. And so the sounds produced by some recreation can affect other people's recreation. And that could lead to some sort of a conflict. So again, the idea is we're trying to develop good policies that can be used in natural environments, either state parks or national parks. And we've been working with those folks to develop acoustic models that they can use. So the basic idea is to understand the input, and by understanding the terrain of the park, use digital elevation mapping. And we're doing simple calculations with the ISO 9613 Part 2 international standard for outdoor sound. That's actually a barrier standard, but we're extending the use of barriers for that to be used for terrain. And the outputs you get are sort of sound maps, as you can imagine. And again, for a park manager, they're going to have a lot of trouble trying to develop sound maps like this on their own. They don't have a lot of money for consultants. So we're developing the software to make it easier for park managers to be able to make their own sound maps. You just input a GIS model. So again, you've got to start with a GIS model, and they're available freely from most states. You get a digital elevation map as part of that. And it can be loaded into a program like ArcGIS Pro and then exported into a system that can be read with like a Python, which is a shareware type of system that you can use. Again, we're using ISO 9613 Part 2. For those of you who do outdoor sound, you already know this very well. Again, you compute the attenuation by adding up a number of different contributions to it. And again, we're using the barrier or screening algorithm to take into account the elevation changes. So again, mostly we're focusing on the atmospheric absorption part and the screening part. We're not spending so much time on the other aspects for this particular project. So under a previous graduate student, we were able to, Nathan Tipton, we were able to develop a sort of a two-dimensional barrier model and use it for applying it to terrains. Again, in previous work, we were able to develop sound pressure level maps using this way, but also working with our colleagues in the Department of Recreation, Parks and Tourism Management, also able to develop other scales which have to do with how would someone actually using a motorized vehicle like an ATV feel versus a person who is a non-motorized user like a hiker or something like that. So we've actually had some subjective scales developed and we wanted to show those as well. So again, based on the additional work that Ed Waite did, and he did a great job with these things, he was able to develop an updated set of sound maps that had some improvements in things in them. If you want to know more about that. No, I'm not giving a poster at the poster session, but if you have any follow-up questions for me, you can ask also me at the poster session. I look forward to talking to you all tonight about that. The specific thing that we were interested in is the ATV noise. So we got a generic ATV sound signal. You can see its time sequence and spectrum right there, as well as in third octave bands. You can get an idea. This is one of the state parks in Pennsylvania. For those of you who don't know it, it's the Tyadotten State Park. And if I can point this out, this river going down through the middle is called Pine Creek. So this is the gorge around it is called the Pine Creek Gorge. Some people call this the Grand Canyon of Pennsylvania. So this is the state park immediately to the west of the Grand Canyon of Pennsylvania. There are 5 locations that are typically used for ATV recreation. And so we take all this in ArcGIS Pro, output it as a digital elevation map, and then here's the results. So as you can see for these particular cases, this is in sound pressure level, and you can definitely see they follow a little bit the topography, but probably less than you think they might. And so this is one of the outputs we were giving as an example. Also, for the difference between the motorized users and the non-motorized user, these are the acceptability maps. So again, if you're a non-motorized user, boy, you'd like for that ATV noise to be constricted. If you're a motorized user, it extends out over a greater region. So again, we have the software, it is available, and this is just an example of what it can do. So again, Atv was able to develop this outdoor sound propagation method. We're able to take in the new inputs for ATVs. And again, we think that the software could be used by park managers and other folks like that to be able to do a better job of managing what's going on within their park. So again, I'd like to thank Atv. If you want more information, you can ask me later, or we can show you where his thesis is available online. So again, on behalf of Atv, Nathan and the team, again, we'd like to thank you, and if you have any questions, let us know. Thanks.
Thanks, Vic, and Michelle and Steve. Steve had to run off to teach class, as you heard, but I think Michelle's still here. We got time for questions. Again, if you have a question, somebody will get you a microphone. Yeah, oh yeah, here, I'll just walk over, I'm close.
Does it have any inputs for man-made structures like urban environments?
Can you repeat that? I'm sorry.
Does it have any inputs for man-made structures like buildings, for example, or is it just topological?
At this point, this is all numerical, and it's all done just with terrain. So we would include a structure by including it in the terrain map at this stage. Yeah.
Others? Yep.
Looks like the updated prediction was a lot wider of a circle, whatever that graph was. So what was the big difference between the old prediction and the new prediction of that acceptable region?
Correct programming.
That is important.
Yeah.
Okay, yeah, I'm not an expert in any of this, but I see a lot of people in the international noise community using sound plan. Is that sort of a similar procedure, or is it different from this?
So there's several large commercial programs that you can get to do outdoor sound propagation maps and things like that. Many of those are developed in Europe because in European, every city has to have its own sound map. There's several different programs which are available. Sound Plan is one of those. The thing is, parks can't afford that kind of expensive software. So this is considered to be an open source version that is less expensive for someone who can't buy those nicer programs, which are expensive, to be able to do some very simple calculations.
Okay,